Hello, everyone. It's a great pleasure and honor to be here with you. We have a Data Science Summit Machine Learning Edition 2024, and we're about to begin the first keynote talk, and will be delivered by Wojtek Kuberski. This will be about the hallucination-free large language models. It's my honor and privilege to welcome warmly our first speaker. Wojtek, the floor is yours.
Thank you for the introduction. So yeah, let's get started without further ado. And as Adrian already mentioned, today we're going to talk about detecting and mitigating hallucinations in LLMs. First, a bit of a background, why me? Why should I be talking about it? First, we run a company, or I run a company called NaniML when we do classical machine learning monitoring. So we monitor models that are deployed to production that deal with classical tasks such as prediction of classification or regression problems. We're also currently building a hallucination detection tool for large language models. And to do that, we've read and evaluated and implemented hundreds of papers. There's going to be results at the end when I show you what exactly we did and what are the results of that. But before that, let's talk about the agenda. So today we have 6 items on the agenda. First, we're going to talk about what is LLM monitoring. So we're going to discuss what are the types of LLM monitoring and where hallucination detection lies. Then we're going to discuss 4 different kinds of algorithms that so far were discovered or invented, depending where you lie on that discussion. The first one is going to be LLM-based hallucination detection, when we're going to look at the consistency of the answer. Then we're going to again use LLMs to detect hallucination of another LLM or even the same LLM by directly asking LLM to evaluate the answer. Then we're going to talk about 2 types of LLM hallucination detection that are based on using predicted probabilities for every token. First one is going to be the output uncertainty quantification, which is a very simple benchmark method that works really well, works really fast, but it's not that great. And then we're going to talk about the last idea, which is the semantic uncertainty quantification, which takes a bit longer to explain. So I'm going to do that at the right slide. And then at the last part, we're going to look at the experiment results, comparing some of those ideas. And we're going to have a quick Q&A at the last 5 minutes of the talk. So what is LLM monitoring? There's basically 3 LLM monitoring types. First, we can monitor the infrastructure of an LLM. So the uptime, latency, making sure that LLM actually is returning answers, is actually taking our prompts, and how fast it's doing. Then we have usage monitoring, when we can monitor everything that's related to actual interaction with the users. The conversation length, the typical sentiment, both from the LLM and from the user, and topics, to make sure that the topics that are discussed are actually relevant to the way LLM was trained or fine-tuned. And then last thing is monitoring hallucinations. So then we're going to be monitoring incorrect answers, incomplete answers, vague answers, basically everything that has to do with quality of the answers of the LLM to the prompt that our users give to that LLM. And today we're going to be focusing on hallucinations, and everything else is more on the software engineering side. So it's honestly not that interesting. So in terms of evaluation scope, how do we detect hallucinations? We can do it in kind of 4 different ways. We can evaluate the full answer. So we just look at the entire answer of an LLM, and in one go, we will try to see whether that answer is hallucinated or whether it contains hallucinations. This has a very nice benefit that it basically says whether the answer is correct or not. However, it's quite hard to do, and it's generally not very actionable. If you get a 3-paragraph answer and you know that there is a hallucination there, it doesn't help you very much. It doesn't help you solve the problem. It's a good diagnostic tool, but it doesn't really help you solve the issue of hallucinations, so it doesn't mitigate the hallucinations. Secondly, we can look at the answer paragraph by paragraph, when we will, for each paragraph, say whether this paragraph is hallucinated or contains hallucinations. Again, we get a bit of interpretability, but it's not fully there. And we're losing a bit of diagnostic power because we need to run it separately for all paragraphs. And in some edge cases, it might be that each paragraph separately is actually correct, but the fact that they follow each other implies some kind of hallucination. Then we can do the same thing for each sentence. And I guess you right now kind of catch the idea. Again, we lose a bit of diagnostic power, but we gain interpretability and actionability. And last thing is each token, where basically we lose all the diagnostic power. We never know whether it's actually correct or not. So generally speaking, most of the solutions focus either on paragraph evaluation or sentence evaluation. Full answer is not actionable enough, and each token is really kind of useless. Now, in terms of the actual algorithm, now that we've defined our problem, we can talk about the families of algorithms that exist. So I'm not talking about one specific algorithm here. We're going to be always discussing specific families of algorithms where you will have different ideas, different details of the implementation, and we're going to be focusing on high-level ideas here. And sometimes one specific implementation, just to give you an intuition and an overview how detection works for that family of algorithms. Then we have basically two kind of meta families where we can use an LLM to evaluate the quality of another or the same LLM. And here, as I already mentioned, we're going to be talking about consistency and direct answer evaluation. Or we can look at the uncertainty of the answer. So we're going to be looking at probability for each of the tokens that's returned, and we're going to be using it somehow in some way to quantify the uncertainty and quantify the likelihood of the answer, sentence, or paragraph being hallucinated. So now let's focus on the first part, which is LLM, and we're going to be talking about consistency first. So let's start always with an example. I'm going to be giving always first the example, and then we're going to be delving deeper into the actual algorithm. So imagine that we have a prompt that says how to detect hallucinations in an LLM. And what we can do is we can ask an algorithm, an LLM, which is an algorithm actually, 3 times the same prompt and just vary, for example, the random seed, and we'll get 3 different answers. And then we can somehow, and again, this is one of the kind of toggles that we can move and we can details that we can adjust. We will somehow compare the similarity between these 3 answers. And then we're going to get a number that generally should be between 0 and 1. And then the intuition is that the more similar those answers are, the more confident the algorithm is, the LLM is, that this is the correct answer. If we ask a high quality LLM, what is the capital of Poland? We're gonna get answer Warsaw, probably 999 times out of 10,000, or even 10,000 out of 10,000, that it's Warsaw. So the algorithm is very, very confident of that. Whereas if we ask for something that nobody knows about, then the algorithm will probably just answer randomly every time, and each answer is going to be random. And we're using that intuition here to try to detect hallucinations. Then basically, there's of course pros and cons here. First pro is that it doesn't require access to probabilities, so we can work with LLMs that do not return probabilities, such as ChatGPT, and a few more closed source LLMs also don't return token probabilities. It generally has good performance. It is able to detect hallucinations quite well compared to human ground truth. However, it does require multiple calls to an LLM. We're going to be asking the same LLM we're using multiple times, and that generally tends to be quite expensive. So it's quite limited in terms of real-world applications. Now, we have kind of 2 levers here that we can adjust. One lever is how do we get different answers? Second, as I already mentioned, is how do we evaluate similarity? Now focusing on the first one, how do we get different answers? We can do it in 3 ways. We can change the seed, which is generally speaking the preferred option and something I've seen in, I think, most of the papers that try to solve hallucination detection with that approach. We can also adjust the temperature, so make the LLM answer more or less random, but it doesn't really have the same consistency. And if we increase temperature too much, we start getting hallucinations all the time. And then we can paraphrase the prompt, potentially with an LLM, just asking it to paraphrase the prompt and ask it again, which is a valid approach. Definitely better than adjusting the temperature, but it means that we need to call an LLM yet another time, so it increases the costs further. So again, not something that's used widely in the real world. Then the second lever we have is measuring the consistency, measuring the similarity between different LLM answers. The easiest way to do it is to give the prompt, give, let's say, 3, 4, 5, however many answers we decide to go with, and just call the LLM again and ask how similar those answers are. Give it to me on score 0, between 0 and 1, or give me a score between 0 and 10. And that surprisingly tends to work very well. LLMs are generally very good at evaluating the similarity of two texts because, I mean, they work with text, they're really good at that. Another option, much simpler option, but not necessarily that great, is cosine similarity. There's recently been a bit of controversy in terms of whether we can actually use cosine similarity to evaluate whether two texts are similar, but it works well enough. We are able then to compare. So basically, we're going to embed all the answers, and we're going to compare similarity in the embedding space. And then third option is to use something kind of in between, to use kind of, how would I say it, small LLM, something like BERT, and then use that to evaluate the similarity between models, which is kind of a middle ground. Generally speaking, most people just call an LLM another time, since we already called it multiple times. One more is not such a huge cost compared to the cost we already bear to monitor an application. And here I have an example paper. I'm going to take a screenshot now. And I will always give an example paper with an example implementation. Generally, it should be either the most popular paper or the first one that implements a given family of algorithms. Here it's self-check-GPT. Now we move on to the second part, which is answer evaluation. So what we're going to do here is we're going to directly ask an LLM to evaluate whether this prompt and this answer are correct, complete, and, for example, grammatically correct. And we can now we need to create another prompt on top of it that basically will prompt the LLM to evaluate the quality of its own answer given the original prompt. So we'll have to ask specifically about grammar structure, about correctness, about vagueness, and about ambiguities, etc., etc. That means that we can include custom metrics. We don't have to say only whether this contains hallucinations, give me one number, but we can go crazy. We can basically ask an LLM about anything, which is potentially useful because we might want to make sure that the answer is not only correct, but also complete. It might be actually more important than just correctness or unambiguity. Again, we don't require access to probabilities as with all LLM-based methods, and we have very good performance in terms of actual hallucination detection, actually better than any other metric. And it requires just a single additional call to an LLM, but we have a complex additional prompt, so there is a bit more work on prompt engineering, but luckily there is less cost. So this is one of the methods that's actually used in the real world. It's used in practice since costs are, generally speaking, a bit more than double of just normally using an LLM because the additional prompt tends to be longer, and we need to include the original prompt and the original answer in the new prompt. But it gives really good performance. It works quite well, and it's not that expensive. And again, here we have an example paper called LLM Eval. Again, take a screenshot and I can also post it later on in the answers if you need to. Here we have just one lever, if I remember correctly, which is what LLM should be used as the evaluator. And one option is to use a simpler LLM, which will help us drive down costs. So then we can make sure that it stays below, let's say, 2x or even 1.5 or 1.3x the original cost of using an LLM. If we're using something that's really simple and really cheap to use, whether open source or closed source. But of course, then we're dealing with the fact that we have decreased quality and the LLM might not be able to properly evaluate the answer of a more complex, more powerful LLM. We can also use the same LLM, which generates the simplest method from the engineering perspective, because we already have everything set up, again, whether closed source or open source. We already have all the APIs set up. For open source LLMs, we already have the machine that runs that LLM. So it's the simplest to implement and it's generally preferred option. And you could potentially use the best LLM available, even better than the one you're using. But then why not just use it to actually get better quality answers? So that is definitely not recommended. And here, so these were the LLM-based approaches. Now we're going to talk about the uncertainty-based approaches. So we're going to be working with probabilities. Now we always require access to token probabilities. Yep. Yeah, I have too many, filler slides. Anyway, let's start with output uncertainty quantification. So we're going to be looking at token probabilities of each of the tokens. So you see here, you can use another LLM. There's going to be you, there's going to be this for you, and there's going to be this for the comma. So we have output probability for each of the chosen tokens. So LLM is going to choose semi-randomly the tokens to create an answer based on the probabilities it outputs. And we're gonna then use those numbers in some way to try to quantify how uncertain the algorithm is itself, how uncertain the LLM is itself about its own answer. So here, instead of calling LLM again, we're gonna be using auxiliary additional output of an LLM, which is the probability, to somehow quantify whether there is hallucinations there. Yes, we require access to chosen token probabilities. So for each token that actually we have in the answer, we require access to that one. So we cannot use this algorithm, for example, for ChatGPT. Good thing is that it is really cheap to run and it's very easy to implement. It doesn't require additional LLM calls and can be basically implemented in like 5-cell Jupyter notebook. There's maybe 20, maybe 30 lines of code at most here. So it is very cheap to run. It gives an okay performance in a way that the hallucination detection correlates with human answers, but it's not a huge correlation. So it will be able to pick up some of the issues, but not all of them. There is an example paper, which is an actual survey paper. So there's lots of different algorithms there, and it's one of the benchmark ones that's also implemented there. So if you're interested in the details, go ahead there. And now we go to the levers that we can pull, the things that we can adjust when it comes to output uncertainty quantification. So the first question is, how can we take these numbers and turn it into one number that will tell us what is the probability that a given paragraph is hallucinated? So what is the probability of the hallucination given the token probabilities? And we can approach this from multiple perspectives. The easiest kind of benchmark approach is to just take these numbers and average them in some way, or take some kind of summary statistic of these numbers. Of course, this is not the only way, but it's one of the ways that doesn't require us to train any other models on it. And we can take average token probability, we can take a geometric mean token probability. Geometric has a bit more intuition here because basically these LLMs are autoregressors and one answer is based on the other. So one token is based on all the previous tokens. So this kind of approach, when we just multiply those, kind of makes sense. And then we can also take just the minimum. And the idea here is that even if there is one incorrect token here, the entire answer is probably incorrect. So we should just look at very uncertain tokens. And here, looking at this example, this is indeed the case, where the last idea that you can just build the random forest to detect hallucinations without giving any details, that's a hallucination. That is one of the things that I haven't seen anyone try to do. So here, just one uncertain token already indicates that there is hallucination, and minimum token probability and geometric mean token probability are generally the benchmarks that are used. But again, it's something that you can absolutely deploy to production as an MVP because it's going to be super cheap. But you should be aware that it is better than doing nothing, but it might not be good enough if your application is really critical and you need to make sure that there are no hallucinations in an LLM. Now we go to the last family of algorithms, which is the semantic uncertainty quantification. That one would take a bit longer because it's quite complex, to be honest, but super interesting idea. So what we're going to do here is, instead of looking just at the chosen tokens, we're going to look at, let's first say, all of the possible paths that the algorithms could have answered. And of course, looking through it all is absolutely impossible because we get combinatorial explosion or exponential explosion, I think. But let's say we ask, what is the capital of France? And then for each of the tokens, we're going to take top three most likely tokens. So let's say that the most likely answer is Paris as a first token. And then we'll look at one level deeper after Paris. What is the three most likely tokens? Maybe is, maybe are. And we keep on building this kind of ever expanding tree. And then we're going to use that number in the entire tree somehow to actually quantify the uncertainty of the algorithm. So to again answer the question of what is probability that the actual chosen answer is hallucinated. And the reason we want to look at this entire tree comes from this example. So we have a prompt, what is the capital of France? And now we get three answers. The first answer is the capital city of France is Paris. This is one answer that could be generated. Second answer is just simply Paris. It's a very concise answer. Third answer is the capital city of France is Rome, which is obviously incorrect. So the first two answers are correct. Now imagine that our LLM actually returns the first answer, but it is very, very uncertain between the first and the second answer. So the probability of the first token being D and then following capital city of France is Paris is like 0.4. And then Paris is like 0.30 something. So the algorithm at the first glance is actually very, very uncertain about the answer. But actually from human understanding level, it's not uncertain about the answer, but it's uncertain about how to phrase it, which doesn't have anything to do with actual hallucinations. It's just the algorithm doesn't know how to phrase the answer. And this is something ideally we would like to capture somehow in our algorithm. So what we're going to do is we're going to look at all possible answers, and we'll look at semantically equivalent answers, and we're going to kind of bag them together. So we're going to put answer 1 and answer 2, which are semantically equivalent. We're going to put it together, and we're going to count it as the certainty of answer 1. So if we bag those together, then suddenly the probability of the first token is 0.8, which is much higher and tells us that actually the algorithm is quite confident that the answer is Paris, and we can say that the answer is not hallucinated. And that brings us to one of the kind of cheap levers that we can adjust here, which is what does it mean that two answers are semantically equivalent. And here again, for better or worse, LLMs to the rescue, because we see that the first answer and second answer are semantically equivalent, whereas first answer and third answer, despite only having one word difference, which is Paris or Rome, are not semantically equivalent. They are actually completely different semantically. So here we need to ask some kind of language model. It can be an LLM, it can be some simpler language model, to also evaluate the semantic equivalence or semantic similarity between the answers given the prompt. So let's talk about the details again. We're going to calculate the probability of getting to a chosen answer or semantically equivalent answer. So again, blah, 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 Paris or just Paris. Pros and cons. We do acquire access to all token probabilities, not just the chosen token probabilities, but all probabilities, which pretty much means, I mean, all is of course here in, not really all, but certain, let's say, 90% of all probability mass, we want to get access to those token probabilities. So we require more than the chosen token probabilities, which means that we pretty much can only use it with open source LLMs when we can get really any kind of answer we want. Which also means that it is rather expensive to run, because even though we can only use with open source LLMs, we'll need to get all those token probabilities, and then we'll have to also compare those. And we'll need to build this exploding exponential tree of possible answers. Good thing is, though, it doesn't require additional LLM calls. So for anything that requires super high security and privacy, and you don't want to send your prompts anywhere, then it is definitely a valid idea. And kind of the most beautiful thing about it is that it does incorporate the full semantic meaning of words, sentences, and paragraphs. So we're not only looking at one single answer, but we're looking at everything. And then the last thing, it does have good performance, unsurprisingly, since we're really looking at more than just numbers. We're looking at semantic meaning here in some way. There is a paper here again. You can take a look at it if you want to go more into details of the implementation. Now, in terms of the levers, there is one more, which is when do we stop? How deep do we want to explore this potential tree? One heuristic is that we want to capture, let's say, 90% of total probability mass. Here, by total probability mass, I simply mean that we want to get all the answers on the possible answers in the tree that in total algorithm is likely to answer with 90% probability. So out of all the answers, we want to capture all of them that the algorithm is more likely to give. And then what is semantically equivalent? As I already briefly mentioned, we should ask an LLM, or we can again look at the two answers and do something like cosine distance in the embedding space. Now, the last thing, since we still have like 1 or 2 minutes, is the experiment results. So what you see here is basically the correlation between the human evaluators for each of the answers. We used, I think, one of the Wikipedia data sets that was scored by human evaluators. So human evaluators said whether the answer is correct, relevant, informative, and then the average. And here we compare it with the LLM eval, so with the second answer, our second family of algorithms. And we see that, generally speaking, human evaluators and LLM evaluator are quite correlated. So we measure just the correlation between those answers, whether they tend to agree. And we see that generally they tend to agree, especially when it comes to average and the correctness. Yes. So here is another approach, the benchmark approach, when we look at just sentence level probabilities and we take the average probability for token probability for that sentence, and we see whether that also correlates with ground truth correctness, and we see that it kind of does, but the actual correlation is much lower, so we can detect something, but we're going to have both a lot of false negatives and false positives. And then the last thing, which is maybe the most interesting, is why not use both at the same time? Here, I'm looking at the correlation between LLM evaluation and the sentence level probabilities, and for the same data set. And again, we see that they are basically not correlated at all, which means that using both in some way can potentially help us capture hallucinations better than just using one or the other approach. So, in summary, hallucinations can be reliably detected and reduced with current technology. There's already algorithms for that. There are two efficient solutions used in the real world given the constraints. You can either just evaluate the answer with an LLM. It's good, it's moderately expensive. We don't need to have probabilities, we can work with closed source LLMs. Or we can just do simple uncertainty quantification when we just look at, let's say, average probability per sentence. It's very cheap, it's very simple, very easy to understand, and it gives okay performance. Thanks for listening now. We still have a minute or two for Q&A, and yeah, leave your contact information. Connect to me on LinkedIn if you want to talk more, if you're curious about how to detect hallucinations. And thank you very much.
Okay, thank you very much. Great. Was a great talk, Wojtek. Clear one. I've tried to grab those hyperlinks that you have provided. Yes, let's take a look. Yes, we have 2 minutes and 6 questions. And if it is not a problem for you, please take a look at the chat. I have provided you with the hyperlink to the wall where you can find those questions. And they are sorted so that the oldest is at the top. Okay? And I will highlight the question. So I think it will be good if you grab this question and provide the answer. Okay? Please go ahead.
You said that you can detect hallucination on various levels, example, paragraph sentences. Are there any other ways? I'm thinking about detecting hallucinations or some type of summary of an LLM answer. Yeah, sure. So you can create kind of a hierarchical answer when you will first summarize the entire answer and then try to detect the hallucination there. But it's basically equivalent from human perspective of evaluating it on the entire answer level. We get the same level of interpretability and the same level of actionability, which is not much because if we do it on the summary, we don't really know what exactly is wrong with the answer itself.
Thank you. I will take this question and provide you with the second.
Could you link some materials, resources, papers on the best way on how to evaluate LLMs? Sure, but I don't know how to do it right now. I would need to
if I can provide you with a piece of advice, you shared just the QR code, right? And you've invited us to contact you.
Yeah.
So maybe it will be best if the people will direct message you about those resources.
Sounds good.
Okay,
yeah, just connect with me on LinkedIn and then I can share any materials.
I will do it as well. Okay, thank you. Question marked as answered. And now we have the question. Let's start with the how can we detect hallucinations in GPT 3.5 Turbo?
Yeah, so here we cannot rely on token probabilities because if I remember correctly, GPT 3.5 Turbo does not return probabilities anymore. So we'll have to go for one of the LLM evaluation answers. So either consistency or looking at asking GPT again directly whether this answer was correct. And that's what I would go for.
Okay, thank you. So this question will be marked as answered as well. Let's fast forward to how the probability should be set up, saying can token is 0.98 and measure is 0.45.
I'm not sure if I follow that question, so I think we'll have to skip it.
Okay, so I think, yes, please contact directly. Okay, ticked. And the penultimate question, in addition, shouldn't we avoid punctuation here as they increase the average results, always being around 0.99?
Yeah, that's a very good question. And in general, yes. Here I was focusing on one of the kind of benchmark implementations when we don't really try to focus on the details and just look at the simplest possible implementation that definitely can be improved further.
Okay, marked as answer. And the last question, so will all VODs be available after the conference? I believe this question is directed to the conference organizers, but if I can precise and put it towards you, so will you agree to share the recording?
Absolutely.
Thank you very much. And I will double check. There are no further questions. Wojtek, it was great. So I think we liked it. So please click the thumbs up. thumbs up, and do not forget to rate this great session. Thank you, Wojtek. I wish you all the best. I can see the sunshine right on your face.
Yeah.
So probably, yes, I think you have a great weather. So have a walk, and have the rest of the day. Thank you very much. I wish you all the best.
Thank you. Thanks,
Thank you.
everyone.
And bye-bye.